Okay, let's talk about the dot product or known as the scalar product. So the idea is that we're going to combine two vectors. We're going to come up with a number. So it's known as the scalar product, but it's also known as the dot product. So in the next unit, we're going to actually combine two vectors to come up with another vector, and then that's known as the vector product. But we're not doing that here. We're combining two vectors to come up with a number. So let's let A be vector A1, A2, and let's vector B be B1, B2. And so we define the dot product. So we define the dot product is a scalar, and we say it's equal to A1 times B1 plus A2 times B2. Now you might say, Mr. Adler, why do you leave that space up there? Well, we could add on a third dimension. Here's A3, B3, and therefore, it would be plus A3, B3. There's always like a third dimension. It exists, we just, on paper we don't have it, but if we could expand it out. We theoretically, not in this class, you theoretically could expand like to 20. And then this idea of a dot product is, something else. Now in this class, so once again, bring it back, 2 dimensions, 3 dimensions. So let's just do an example. So I want to go back to my blue pen, sorry. So let's let A, example 1, let's let A be 1, 2, and let vector B equal 3, 4. Whoops, not a fraction. Therefore, the dot product is equal to 1 times 3 plus 2 times 4, and that's equal to 3 plus, this is 11. Obviously, this is going to have implications. In this class, it's going to have geometric implications, but let's continue. How about we let C be, 2i plus 3j, and we'll let D equal 5i minus 7j. So the dot product, the scalar product, is a number, and it's clearly 2 times 5 plus 3 times negative 7, and that gives us a negative 11. Once again, it means something. We can do this in 3 space. Let me move my screen down a little bit. So let's see. Let's let E equal to 1, 2, 3, and let's F be the vector negative 3, 2, 1. Therefore, the dot product is equal to 1 times negative 3 plus 2 times 2 plus 3 times 1, which is 4. I'm going to show you how to do all of this in the calculator in a video at the end of this video, but let's just go a little old school, part 1 today. Let's see. So the question now is, the next thing is, with the dot product, we can now find the angle between two vectors. So using the dot product to find the angle between two vectors. Now this is kind of cool. You're given the formula, but let me derive it for you. Let me show you how it does. So the idea is we have 2 total random vectors, and we're going to put them like tail to tail. So we have vector A, and we have vector B. Okay. Well, and A could be, let's keep it in 2 dimensions, and you know that we can expand it to 3 dimensions. Let's keep it in 2 dimensions. So we have A, B with this angle between. Well, let's see what we can do. Well, you know what? I could create the vector here. And we know because it starts at A and ends at B. So what is this? Well, it starts at A and ends at B, or we visually know if we're starting here, I'm going to refer opposite A, regular B. So this is B minus A. Okay, so can we hook all these together? And you're like, yeah, because once again, so we say the magnitude of B minus A squared is equal to the magnitude of A squared plus the magnitude of B squared minus 2 times the magnitude of A times the magnitude of B cosine of theta. We can put this together, right? They're regular numbers, right? They're just lengths. And since we know the vector, so B minus A, well, I don't know what B and A is, but I do know that B minus A is I know that B minus A is, B1 minus A1, B2 minus A2. So the magnitude of that is B1 minus A1 squared plus B2 minus A2 squared. You don't have to write this down, but once again, this is the derivation. This is equal to, A1 squared plus B1 squared plus, A1 squared plus A2 squared plus B1 squared plus B2 squared. I'm going to leave this for a reason. I'm going to leave it for a reason. So we have minus 2 magnitude A, magnitude B, cosine theta. Okay. Some algebra. As I said before, you get the formula for this. You don't need to go through all of this, but this is where it comes from. Let's expand this out. We have B1 squared minus 2A1 B1 plus A1 squared plus B2 squared minus 2A2 B2 plus A2 squared equals, I'm lazy, I'm not writing this whole thing out again. This whole thing goes down there. Now, you say, oh, you know what, there's stuff on the left, and let me get my red pen. There's stuff on the left that can cancel out with stuff on the right. Let's see, what goes out with what? Well, the B1 squared goes out with the B1 squared. The A1 squared goes out with the A1 squared. The B2 squared goes out with the B2 squared. And the A2 squared goes out with the A2 squared. And I am going to write the next line out. And we have, you can see here, we have negative 2A1 B1 minus 2A2 B2 is equal to negative 2 magnitude A magnitude B cosine of theta. Let's divide everything by negative 2. Divide everything by negative 2, right? And we're left with, this is kind of cool, we're left with A1 B1 plus A2 B2 is equal to magnitude of A, magnitude of B, cosine of C. Well, this is A dot B divided by magnitude of A, magnitude of B is equal to the cosine of the angle. And this is the formula. This is kind of cool. So, if you have, this is awesome, and you got this formula. So again, this is the derivation of it. If you have two vectors, you can find the angle between them. What we're going to see in the next unit is if you have the slope of a line, that slope is the direction vector, and you can easily now, instead of using that difference in tangent formula, you can quit. Vectors makes your life very easy. Let's do an example. Let's get an example down. Let's get an example down. Let's see. We have two vectors. Vector A is 3, 4, and vector B is 2, 1. The question is find the angle between A and B. So you could draw a picture if you want. Oh, sorry. You can draw a picture if you want. I mean, this is like 2, 1. And this is 3, 4. You're looking for the angle here. And you simply say, okay, cosine of theta is equal to the dot product. So it's 3 times 2 plus 4 times 1 over the magnitude of 3, 4 times the magnitude of 2, 1. Well, let's see, the cosine of theta is equal to, what's going on up here? 6 plus 4 is 10 divided by, well, this is easy because the magnitude of the vector 3, 4 is clearly 5. and the magnitude of 2, 1 is the square root of 5. Final answer is 2 radical 5. Theta is equal to the inverse cosine of 2 over radical 5. Put that in the calculator, you get 26.6 degrees. And therefore, now you can find the angle between two vectors. You could do the same thing with we'll do the same thing with something in 3 space. I'll do that in GeoGebra. Let me make a note of that. Good. Okay, so a couple of things you need to know about the cross product. So let's see. What do we need to know about the cross product? The dot product. Let's see. What are some things you need to know about the dot product? The first thing is that important things. First of all, let's use V. The book uses V and W is equal to WV. I mean, and that's obvious because, 3 times 2 is plus 4 times 1 is equal to 2 times 3 plus 1 times 4. So this is the commutative property. This works. Number 2, this is kind of cool also. The dot product of a vector times itself is equal to the magnitude squared. This is going to show up. Just know this. It shows up on these little, they want these little theoretical parts. That kind of makes sense if you think about it. Let's let V equal, V1, V2. That means V dot V is equal to V1 squared plus V2 squared. Well, this is the magnitude of V squared. So that's where this theory comes in. It ends up being, it'll show up, I guarantee it. Number 3, they want you to know that it works for the distributive property. So if you do the dot product of the sum of 2 vectors, it's like taking the dot product of each of the vectors. And algebraically, you can figure that out on your own. That might show up, probably not. Good. What else do they want us to know? They want us to know that, here's another interesting thing. They want us to know that if you have a vector that's multiplied by a scalar, and you take the dot product times V, you can pull out that scalar and then do the dot product. Maybe K is some crazy number like -8.9. Pull out the K, and you'll see it. The idea is you can just quickly take the dot product and then multiply it by the scalar. What else do we need to know? Okay, so let's get back to that. So we have these properties. Let's get back to the angle, because this is kind of cool, because the question is, can we tell the type of angle just by looking at the dot product? The answer is yes. So let's think about it. Number 1, let's talk about the angle. So if the dot product is 0, that means the cosine of theta equals 0, and therefore theta equals 90 degrees. And so if VW equals 0, then V is perpendicular to W. This is kind of important. And it's also the flip side. So, for example, they might say, is 2, 1 perpendicular to -4, 8? And you would say, maybe. And you're like, fine. 2 times -4 plus 1 times 8 is equal to 0. Therefore, yes, 2, 1 is perpendicular to -4, 8. And then they throw in these problems. This is probably a little more SL, but actually, they took this out of the SL curriculum this year. But it might show up. They might say, find B so that 3I minus 2J minus BK is perpendicular to BI plus 3J plus 7K. So it's an algebra problem. You have to know this property. If they're perpendicular, the dot product is 0. So you just set it up. You're like 3b minus 6 minus 7b equals 0. Negative 10b equals 6. B equals 3 over 5. So when b is 3 over 5, these two vectors are perpendicular to each other. Is there any other cases? Well, yeah, there's a whole slew of angles that the angle could be. I mean, we're considering, yeah. So let's think about this. What other options are there? Well, there's acute, there's obtuse, there's parallel. We know from our law of cosines, law of sines, we're not looking at 250 degrees. We're not interested in that in this. So the question is, well, let's think about this formula. So we have the cosine of theta is equal to, well, let's use our V and W. So we have V over W, the magnitude of V and W. Well, these are magnitudes and these are squares. So first of all, we know that the magnitude of V and the magnitude of W is greater than 0. So that denominator is positive. So the thing is, what's going on over here? Well, we know that cosine of theta is positive in the first, and we know that the cosine of theta is negative in the second, right? So if the dot product is greater than 0, then we can say that theta is, well, first of all, once again, knowing the denominator is positive, if the dot product is positive, the cosine of theta is also positive, and therefore theta is acute. What else? If the dot product is negative, that means cosine will be negative, and theta is obtuse. Theta is obtuse. Okay. Other options? Yeah. What happens if it's equal to 1, right? Or cosine of theta equals 1 or negative 1. What's going on there? Well, the idea, if it's 1 or negative 1, it's like parallel. So it's like here's two vectors, right? If they're multiples of each other, yeah, the idea is that they would be parallel to each other. Yeah. They would be parallel because if let's let this be double V, and let's let this be KV, right? So we have V dot KV over V dot KV, right? Because that's the cosine. Right? Yeah, this is interesting, right? So, if we pull this out, we have K. Nice. If we pull the K out, we have K times V squared over the absolute value of K times V magnitude. This goes out with that. And so we have two options. If they're parallel, that means if they're parallel in this, if they're parallel, then K equals 1. If they're opposite directions, right, then K equals negative 1. And that's the two options. So if it's 1 or negative 1, either they're parallel or they're in opposite directions. But the idea is that they're multiples of each other. Nice. I thought of that myself. What else? I think that's it. So you're just going to work on 14J. In 14J, the last thing they talk about is they give you these figures, and they say find the measurement of angle so and so. They'll say, find ABC, and they put this notation on the beat implying that B is the vertex. If they want you in vector world, if they want you to find the measurement of angle ABC, first find vector BA, and then find vector BC. And then when you have these vectors, you can use the cosine rule to find the angle. And that's basically it. So good luck with the exercise. Right now I'm gonna make a video of how to do vectors in the calculator. I'm gonna show you how to do it in GeoGebra. Okay, so let's use the GDC to do all the stuff because it might be a part 2 question. It might be really easy. So first thing we're going to do is we're going to create vectors. So we go to menu, matrix vector. We're going to create a matrix. And so the rows are the number, whether it's 2 or 3. In this class, either 2 or 3, we only have one column. So let's keep it simple. So 2, 1. And so what we're going to do is first we're going to use the example we did in class, which is you're going to enter 3, 4. What you're going to do is move the arrow over here. We're going to store it. Control var. We're going to store it as the letter A. Hit enter. And then we're going to create another matrix. Menu, matrix vector, create matrix. 2 rows again, and this time it's 1 column, same thing. And the other matrix we had, the other vector we had is 2, 1. Now they used to teach matrix in the class, but they got rid of it. So it would be something interesting to do for your exploration. We're going to store this as B, so control var B. Enter. Now it's kind of cool because we can actually do some algebra with this. So we can do, A plus B. Enter, we get 5, 5. 3 plus 2, 4 plus 1. You could do, B minus A. Enter, we get -1, -3. So you can do algebra in the calculator. The next thing we want to do is we want to find the magnitude of the 2 vectors. Please recall that A was 3, 4. So what you do is menu, matrix vector, scroll down over here to vector, and then there's a couple of things. Oh, I'm sorry. No. Let's go back. I apologize. Go to norms. I apologize. Norm. The norm of a vector is the magnitude of the vector. Let me get my face out of there. You don't want to see my face. The norm of a vector is the magnitude. So that's how you find the magnitude of a vector. Once again, let's do for B. Menu, matrix vector, number 7 is norms. We're going to find the norm of B. But so B was what? It was 2, 1, so we know it's radical 5, which is what? 2.2, what is it? 2.236. That's the square root of 5. So that's how you find the norm. The next thing we did was find the dot products. So once again, we've stored 2 vectors. They could be 2 dimensions. Whoops. They could be 2 dimensions. They could be 3. They can be 2. They can be 3. They can be 11. Once again, theoretically, that's what this is for. But once again, we're just doing it in 2 space, 3 space. So let's find the dot product of these 2 vectors. Well, we know. Let's see. We know from the work that it was it was 10. Yeah, 3 times 2 plus 4 times 1. Well, let's do it in the calculator. Menu, matrix vector. Let's scroll down to vector, dot product. And so we want A, comma, B. That's how you enter it. That's the computer programming access. So once again, we know that it's 3 times 2 plus 4 times 1. It should be 10. Answer is 10. And we could do, let's do a control escape. Let's prove, let's do B comma A, 10. So we prove that the order doesn't matter. The next thing we want to do is use the GDC to find the angle between these 2 vectors. And so we knew the formula is the cosine of theta is the dot product divided by the magnitude, the product of the magnitudes. So let's stick that in there. Trig, inverse cosine. I'm going to put the dot product on the top. So let's see, menu, matrix vector, scroll down, vector, dot product of A comma B, go outside the parentheses, divided by, open parentheses, I want the norm, right, because it's the magnitude, so I want matrix vector, norm of A, times, times the norm of B. Let's close out. Let's see. Let's hopefully. Let's see. Do we have this right? We have the dot product on the top. No, I think I need another parenthesis. Let's see. Let's see what happens. Nice. So we see what it did. The inverse cosine of the dot product over the product of the magnitudes, 26.56 degrees. Please remember, I have my thing in degrees. The last thing that once again, this it can do it for you. The last thing I want to do is those questions where it's like, here's two vectors, find the value where it's going to be perpendicular. So let's look at that last problem. So let's see. We wanted to find B such that the two vectors were perpendicular. So let's set up an equation. So I'm going to algebra, numerical solve, right? What we're going to do is I want the dot product, menu, matrix vector, create a matrix. This time it's going to be 3 rows and 1 column, okay? And I'm going to do, so the first one was 3i minus 2j minus bk, so I'm going to do 3. Oh, you know what? Sorry, let me back up. I forgot to do the dot product. I need to prove that the dot product is 0. So first thing I'm going to do is I'm going to do menu. Sorry about that. Matrix vector. Go scroll down. Vector. Oh. Whoops. Dot product. And I'm going to put in the two vectors. Now you might think, can I save them? You can't do that. You can't save vectors if there's variables in the vectors. So I'm going to menu, matrix vector, create, 3 rows, 1 column, okay? The first vector was 3i minus 2j minus 3k, so it's going to be 3, negative 2, and b. So let's make that x, actually. And then I'm going to do comma. I'm going to put another matrix in there. Let's see. Menu, matrix vector, create, 3 rows, 1 column, okay. In this case, the second vector was bi plus 3j plus 7k. But instead of b, I'm going to use x, 3, and 7. And I need the dot product to be equal to 0, comma, x. And the question is, can the calculator solve this? Once again, we were given 2 vectors, and we need to find x so that they're perpendicular. Hit enter. 0.6 or 3 over 5. Nice. Very good. Next, I'm going to show you what these vectors look like in 3 space.